In this video, we're going to talk about indefinite integrals, and I'll explain what they are a little bit later. First, we need to find what is called an anti-differentiation. So we're going to be doing the opposite of what we were doing with differentiation. And before I tell you the rules of how to find the antiderivative, we're going to try and find what the pattern is for all of these. So let's go ahead and use our differentiation rules that we already know and find the derivative of all of these functions. So we're going to have the derivative of x to the power of 4 is 4x to the power of 3. The derivative of 2x to the power of 4 is 8x to the power of 3. The derivative of this one is, the derivative of this is going to be 4x to the power of 3 over 4, which simplifies to x to the power of 3. And the next one we're going to have 3x to the power of 2 over 3, which simplifies to x squared. And then for the final one, we're going to have j is 2x over 2, which is just equal to x. So let's look at the patterns. When we went from our function to the derivative function, we did what's called differentiation. Now today's objective is to find the antiderivative. So we want to go from the derivative to the original function. So there's a few things that we can start to realize. One of the first things we can start to realize is the exponents. Instead of subtracting 1 to the exponent, it seems like we're adding. So there seems to be kind of a plus 1 being done instead of a minus 1, which is going from finding the derivative, right? So that's the first thing that we can kind of start to realize. Another thing we can start to realize is if we look at the coefficient in front. So remember, we're trying to go from this derivative to its original function. Well, another thing we can realize is what is the coefficient. So if we look at the first example of x cubed, that became x to the power of 4, yeah, plus 1 on the exponent. But x cubed now is divided by 4. So we now have something like the bottom seems to be the same as the exponent. And we can see this happening for the last 3 examples. In the last 3 examples, we have the following, where we are looking at the original function was x to the power of 3. And then when we found the antiderivative, we had x to the power of 4 divided by 4. When our derivative was x to the power of 2, we seem to now have x to the power of 3 over 3. So these patterns we're going to be seeing more and more, and we're going to talk about them. Good. Now, before we talk about the final rules that we just found, let's do a couple more derivatives and see what is happening. So if we have this derivative is going to be 3x squared. The derivative of 3 is just 0. The derivative of g of x is also 3x squared. Derivative of 34 is 0. And the derivative of hx is 3x squared as well. Now we have a little bit of a problem because all of these have the same derivative. However, they all represent different original functions. All of these functions are different, right? They have these values that are completely different. Therefore, when we are going to be going, instead of deriving, this way was deriving, when we're going to do the antiderivative, we need to keep this in the back of our minds, that even though all of these derivatives are exactly the same, they represent different functions. Therefore, what we're going to do is every time we are going to find an antiderivative, we're going to have this plus c that we're going to add, which is going to talk about this value here. And this plus c value, eventually we're going to find what it actually is equal to. But for right now, every time that we find an antiderivative, we're going to need to add plus c to represent a potential number that could be added or subtracted to our original functions. Now, we're ready to talk about the rule for integration. The rule for integration is that we are going to have, our function is going to add 1 to the exponent, and then whatever that number is, we're also going to divide it by x to the power of n plus 1 is going to be divided by n plus 1. And then as we just talked about, we need to have a plus c value. And this is what we're going to be using all the time to find our antiderivative. This rule of integration, we have this part here is called our indefinite integral. So indefinite integral. And the reason why we call it an indefinite integral is because we don't have our boundary points a to b like we did for our definite integrals. So the indefinite integral is this symbol here. And the indefinite integral is equal to its antiderivative, which is this part here. So this part is called the antiderivative. And that's really the opposite of differentiating. So now that we know this, we can therefore find what is this integral. Well, the integral of this is going to be, we keep the 3 there as we do for differentiation, and then the integral of x to the power of 2 becomes x to the power of 3 divided by 3, right? And then, of course, every time that we do the integration or we find the antiderivative, we have to add c. So once the integral symbol in dx, once this is gone, that means that we've already integrated, and then we have to add that plus c. And of course, we can simplify this, and the 3's are going to cancel out, and we're left with x cubed plus c. And that's going to be the antiderivative here. Let's practice this. So we have this rule, which we're going to practice for many, many examples. If we look at our first example, we have 7. Now 7 is just a number. And this is a special one because this 7 is like x to the power of 0. Therefore, if I use the rules for integration, I'm going to have 7 times x to the power of 1 over 1. And of course, I've integrated, so I need to add plus c. So the integral of 7 is going to be 7x plus c. And then to make sure that we did it correctly, we can always go from our answer. We can derive this answer, and we should be getting the original one. So what is the derivative of 7x? Well, that's just 7, and then we did that correctly. The derivative of just a number is 0. So we know that we did it correctly. Let's continue. What is the integral of x to the power of 4? Well, x to the power of 4, we need to have x to the power of 5. We're adding 5, and that's going to be divided by 5. I've integrated, so I'm going to have a plus c. Again, if you differentiate this, we would get 5x to the power of 4 divided by 5, and those 5's would cancel out. So we're getting there. Next, x to the power of 4 divided by 4. Now this is the same thing as saying 1 over 4 times x to the power of 4. So I can take the 1/4, pull it out, and then I just ask myself, what is the integral of x to the power of 4? And the integral of x to the power of 4 is x to the power of 5 over 5. I've integrated, so I can add a plus c. And therefore I can simplify this, and I get x to the power of 5 divided by 20 plus c. And I continue for the next one. For this one, we can pull the 2 out, and then we can ask ourselves, what is the integral of x to the power of 4, which is x to the power of 5 divided by 5. Whoops, plus c, I almost forgot to. And then we're going to have 2x, actually, to the power of 5 over 5. We can keep it like that, or as a fraction. A little bit more. Now, same as our derivatives, we can only use this rule for integration when our original function is x to the power of something. In this example here, we don't have x to the power of something, so I need to rewrite the integral such that we have x to the power of something. In this case, rewriting it, I get x to the power of -3. So when I use the integration rule, I'm going to have negative 3 plus 1, so that's negative 2, divided by negative 2 plus c. You can keep it like that, or you might want to write negative x to the negative 2 over 2 plus c. And same thing for derivatives. When we have an addition or subtraction sign between two terms, we're going to treat each integral separately. So I can find individually the integral of 3x squared dx, and then I can find the integral of x dx. So the integral of 3x squared is 3 times x to the power of 3 over 3, plus the integral of x, so that's going to be the integral of x squared over 2 plus c. And this simplifies to x cubed plus x squared over 2 plus c. Good. Now what you've noticed is that when we're doing these integrals, we have the very similar rules to derivatives. When we have a constant only, like our first example, we had the integral of 7. Well, the answer is going to be 7x, or the constant times x, and of course that's always multiplied by c. If we have a number in front, like we have 1/4, we had 2, we have 3, well, what you can do is you can pull the number out and just ask yourself, what is the integral of the function, and multiply it back by your number. And similarly to when we have many functions added together, you can treat them separately and then you can find the integral. Okay, now that we know all these rules, the only one given to you in the formula booklet is this one here, which is our formal integral rule. Let's try 2 more examples. Example A, find this integral. So this integral, I can rewrite it, and I can have the integral of negative 2x cubed with respect to x, plus the integral of 5x with respect to x, minus the integral of 2 with respect to x. So now you can simply take the coefficient in front, and we would have negative 2 times the integral of x cubed. The integral of x cubed is x to the power of 4 over 4. I could decide to write a plus c for every single one, or I can simply have a plus c at the end, which is going to encompass all the coefficients, or all the constants added together. So that's what I'm going to decide to do. I'm going to put the plus c at the end. Then I have the integral of 5x. So it's going to be 5 times the integral of x, which is x squared over 2. And then I'm going to have the integral of 2, which is just 2x. So if I simplify this a little bit, I'm going to have negative x to the power of 4 divided by 2 plus 5x squared divided by 2 minus 2x, and then plus c here. And that is for our first part, A. B right now is not written as x to the power of something. We have this squared in front of all of this. So what we're going to need to do first is we need to expand this function. So we're going to have x minus 1 over x squared. So that means it's times each other. So I'm going to need to distribute, right? So using FOIL, I'm going to distribute. And I'm going to be getting, this is the integral of x squared. Then I have x times negative 1 over x. So that's minus 1. Negative 1 over x times x, that's also minus 1. And then we're going to have positive 1 over x squared dx. Simplifying this a little bit further, I can combine my like terms, x squared minus 2. And then the next one, I need to write this as x to the power of something. So we know that using exponent rules, this is x to the power of negative 2 dx. Once every term is written in the form x to the power of something, I can use my integration rules. So the integral of x squared is going to be x to the power of 3 over 3. I'm going to add the plus c at the end so I don't forget. The integral of just negative 2 is going to be negative 2x. And then the integral of x to the power of negative 2, negative 2 plus 1 is negative 1 over 1. And then, of course, we have our plus c. So if I rewrite this, I have x to the power of 3 over 3 minus 2x minus x to the power of negative 1 plus c.